Yeah, thanks. Yeah, so the basic idea of this talk is that okay, we have all these nice tensor networks, but as we also discussed in Norbert's presentation, can be quite expensive to contract them. And so the idea was to use quantum computers to reduce these costs and use them for something fancy, our nice tensor networks. Okay, so I will try to explain to you how we can use quantum computers to sort of speed up, I mean, that's a big word, speed up simulations of using MERA tensor networks. So these are such hierarchical tensor networks. And then if we have enough time, I will also discuss some recent proofs where we were able to show that the optimization of isometric tensor networks, so this includes these MERAs, MPS, and T-tensor networks, is free of so-called Barren plateaus. Okay, so first the motivation slide we can probably skip. So we have a general state, we think about lattice quantum many-body systems, and we make a nice ansatz for our state in the form of a tensor network, simplest case, these MPS, but we have many different types. So it may be a good idea to simulate a 2D system also with an MPS by wrapping it around a cylinder, as we also heard in Steve White's talk, but you could alternatively use these PEPs, which have a better entanglement scaling. So they reproduce the area laws that you also typically find in the ground states of quantum many-body systems. Or there's also this class of hierarchical tensor networks, which will be the center of this discussion, the so-called multi-scale entanglement renormalization ansatz, which is due to Gueffry-Vidal. And the basic idea is one that's motivated by real space renormalization group. So the tensor network has this hierarchical structure where the idea is that these short range, or these tensors on this first level here encode short range correlations, and the further you go down, the tensors encode longer and longer range correlations.
So we haven't had MERA defined yet in this workshop properly, so maybe you could take a minute to
define the MERA?
Yeah.
Yeah, so the MERA is basically as I said, a hierarchical tensor network, where in each step we reduce the number of sites by a certain factor. And the way we do it is we have some set of unitaries in each layer, acting typically on each on a limited spatial support of, let's say, nearest neighbor sites.
But there's 4 legs with that box.
Yeah.
So how is the unitary acting?
Yeah, so it's a unitary from these 2 sides to these 2 sides, from here to here, from top to bottom.
An arbitrary unitary?
No, that's our tensor. So this is what we will optimize. We will optimize these unitaries in order to approximate the ground state.
Okay, but a priori it's arbitrary, and we're going to make a choice that helps us.
We could impose some further constraints like symmetry constraints and so on, but generally you could say it's a general unitary. Okay. That's fine.
And the isometry, is it also a parameter, or is it?
He hasn't gotten to that.
The isometries are also parameters, exactly, yeah. And the idea is sort of that you have sort of this local decimation of the degrees of freedom. So these unitaries are supposed to, for example, this guy is supposed to disentangle to some extent this half from this half. I mean, it's just local, so it can't do as much, right? But you disentangle them a little bit before you then decimate your state space. And the definition of the MERA would entail that, okay, in each step you decimate the number of sites by a certain factor here too, right? And every layer we decimate the number of sites by 2. Here we have 8 sites. Now here we've gone to 4 sites.
So that
we've gone to 2 sites.
Isometry is an isometry going downward.
Yeah. So it maps from chi squared, so chi times chi to chi.
But then it's not an isometry. It's
a other way around, right? It doesn't matter. Right? Yeah. So it's
a projection.
It's a partial isometry. Yeah. So it's
arrows are pointing up.
Right.
The arrows are pointing up or down?
But the only arrows which are down.
Whatever you.
Oh, I see. So we start at the bottom and we go to the top, or we start at the top and we go to the bottom?
Both directions make sense and are sort of it's useful to look at both directions. So let's say if you say it goes from bottom to top, then we would have this constraint on these partial isometries, right?
I think Jan would be happier if it goes from bottom to top. So.
Yeah, so it's two pictures, right? So if you look in this direction, then it's more the idea of this real space normalization group. If you go from top to bottom, so you decimate your state space, but you can also think of it the other way around, and then it's more like preparing a many-body state. So here you're coming from the bottom, and you're applying, so the unitaries are just unitaries sort of evolving a system. The isometries you could implement by saying, okay, I'm adding sort of some reference state for each side, so another sort of auxiliary system, do unitary, and then sort of continue, right? So you're preparing this many-body state. Okay, and yeah, so you have these guys. The nice thing is you have them in any number of spatial dimensions. Turns out that this here would be a sort of one layer of a 2D MERA. Turns out that these are actually a subclass of PEPs, so you can map a bond dimension chi-MERA to a PEPs with a bond dimension that is independent of the system size. But still, it's a special class in the sense that you can contract these guys efficiently, whereas with PEPs, you need some approximations to contract them. Okay, and yeah, the biggest caveat are the computation costs. So you just show the cost for example, evaluating local expectation value or energy gradient or something. And where it's small, for the MPS, chi to the power of 3, it goes like chi to the power of 10 to 12 or something for 2D PEPs, to chi to the 16 to 28 for 2D MERA. So in practical computations, I think no one is currently using 2D MERA to simulate condensed matter systems. Yeah, and the idea was, can we reduce these costs by putting these MERA guys onto a quantum computer?
Wait a second. You just said that 2D MERA is a subclass of 2D PEPs. You can contract the 2D PEPs in O of chi to the 10 or 12. So why does it go up to?
Yeah, so the reason is that the chi that you have here in the MERA is not the same bond dimension you would have here. So if you map a chi-dimensional MERA to a PEPs, then you get here a bond dimension is different from chi. And also it's a bit like unfair comparison because these computation costs here already entail some approximation. So Norbert showed this picture where you take this PEPs and you contract from one side, and in each step you would truncate. So that's already an approximation, whereas in MERA, this is an exact evaluation. So here you don't need to do any approximations. And yeah, so here's sort of an explanation of how we can evaluate for MERA the expectation value of a local operator. So let's say we have a Hamiltonian that consists of, in this case, nearest neighbor interaction terms, right? So this hi acts on sides I and I+1, and as the identity on other sides. And if you want to evaluate its expectation value with respect to the MERA, then we can exploit that we have these unitaries and isometries, and they cancel, right? For example, if you take these two guys here, so that's u times u dagger, so that just becomes the identity. We can remove this guy. Same for these two guys, and then we would have this isometry. We would be directly connected here. And for the isometry, we have this w dagger times w is also identity. So we can also remove this guy. So all these tensors that are outside the so-called causal cone of the local expectation value cannot influence this expectation value. And we can instead just contract this reduced tensor network, which can be done efficiently. So in this case, for a binary MERA, it would be like the 9th power of chi. If you optimize this contraction order, you would find chi to the 9. And if you go to 2D MERA, you get much higher orders.
Still not sure I understand this.
Sure.
Well, I'm sure I don't understand this picture. So your H hat is acting on
these two sides here, sides I and I+1.
No, but
the total Hamiltonian is acting on all sides.
But your input data is some psi, right?
Yep.
And where is that?
The state psi?
Yeah.
This here is the MERA, the state psi. I call the MERA, I call
so
it
is
psi.
this so this is the MERA where we started from the bottom and went to the top?
Yep.
And so that's how we prepared psi.
Yeah.
Okay. And then we want to...
Yeah, we reflect this sort of to get the corresponding bra.
Evaluate. Okay.
Yeah.
Thank you.
All right. And so this is the first nice property of MERA, which sort of makes them a good candidate to put on a quantum computer, because when we know that, okay, the quantum computers we have in practice are pretty small. But if you sort of just want to evaluate expectation values for MERAs, The same then holds for energy gradients, because you can get energy gradients just from expectation values. This picture shows us that the number of qubits we will need can be independent of the system size, right, of the physical system size. So so we can use a small quantum computer to even like simulate an infinite size system if you want. Yeah, so the system size is just reflected in the number of layers. The number of layers basically is log of the total system size. Okay, then the second nice feature is that sort of by construction or by definition, all these tensors in this MERA tensor network are unitaries or isometries, which are then again nice to implement on a quantum computer, because there we do basically unitary time evolution, right? And so the idea is that we take this such a big unitary, and then typically what you have on a quantum computer is you can implement single qubit and 2 qubit gates. So we impose some substructure where we say, now we constrain these unitaries a little bit, and the question is how important is this restriction. We construct this as a so-called brickwall layer of 2 qubit gates, right? So we say this renormalized site here, which has local Hilbert space dimension chi, we implement by q qubits. So each cable here, small cable now, corresponds to 1 qubit in a quantum computer. So the corresponding Hilbert space dimension is 2 to the q, right? So, and then the action of the unitary is implemented by this brickwall circuit of always alternating layers of 2 qubit gates. And the question is, how many of these layers, or how many, we call this Trotter steps, do we need in order to get sort of an accurate simulation also, or sufficiently expressive MERA? Okay, so now of course contraction costs are much reduced, because we just do unitary time evolution. So if the quantum computer in a sense doesn't care about like how many legs each tensor you had. Just the evaluation time for such a local expectation value is linear in the number of layers, that's capital T, and linear in the number of Trotter steps, that is small t.
Thomas, and then, sorry, can you go one? And then I guess that the unitary is inside of its Trotterized, let's say, big unitary and so on. These are going to be the variational.
Exactly, yeah.
And the ones in the corresponding to the unitaries and the isometries are going to be different in the quantum circuits that you have in the green and blue?
Yeah, so if you want, sort of each tensor could even have completely independent set of 2 qubit gates. So you parameterize each of these tensors by let's say, rotation angles of these 2 qubit gates. And in principle, they could all be different. But in practice, you would probably want to impose like translation variance or something.
So what is the overall goal? We want to find the ground state of H?
Yeah. That I should have mentioned, yeah. We want to find the ground state, yeah. Okay. Right. So now each of these Trotter gates, or 2 qubit gates, you can implement in different forms. So either using C-NOTs, so these guys here, controlled NOT gates, and single qubit gates, or you can also use single qubit gates and then these 2 qubit rotations. That's sort of equivalent parameterizations. Or you could even work in a parameterization-free form, which we call this a Riemannian optimization. But in any case, if you are able to evaluate these expectation values, then you're also able to evaluate gradients. So that's a so-called parameter shift rule. So in order to get the energy, the derivative of the energy with respect to one of the rotation angles of these single 2 qubit gates, you just need to evaluate the energy at different shifts of one of these rotation angles. Okay, and once you have the gradient, then you can do quasi-Newton methods, for example, to optimize your network and minimize the energy to get an approximation to the ground state.
What's CAN?
That's just different names we gave to these two. Actually, it's not important here.
C-NOT is a standard reading.
C-NOT is the name for this gate here, and CAN is just for canonical. It's nothing important. It's just a name. Yeah. Actually, you don't need it for the rest of the talk. I could have removed this here. It's not important. Okay. So the next step is we can. So one issue is, of course, we have our Hamiltonian here has now, if we restrict ourselves to nearest neighbor interactions, the number of terms is linear in the total system size. So in principle, you would have to play this game here for n times, if n is our number of sites. But if you have translation invariance, then we can also exploit this very efficiently here. So the first step would be that we impose that the tensors in each layer here are all the same. So the green ones in this layer are the same, the blue ones are identical. And then you could have different ones for the next layer, but again, this just one type of unitary and one type of isometry, for example. Okay, if you do that, then we can evaluate this expectation value, energy expectation value much more efficiently, because we can implement the sum of all sides by summing over these different layer transition maps. So if you look at the structure here, you will notice that there are only, inside the causal cone, there are only two different maps that occur. And one we call sort of the left moving map, the other is the right moving map. So you always apply first 3 of the isometries, and then you either two unitaries, and then you either trace out 2 sides on the right and 1 on the left, or the other way around. So 2 on the left and 1 on the right. So these are the only layer transition maps, and we will of course then trace out sort of these sides that leave the causal cone. We trace out. So these maps here, they define quantum channels, and yeah, we can, if we want to do this average over all sides here, so the sum of all sides, then this corresponds to taking summing over all possible sequences of these left and right moving layer transition maps. And you can implement this very easily just by defining this map, which is the equal weight, so the convex combination of these two maps, right? And so you just get in one go the total energy. Okay, and this works for all kinds of MERA. So this is a different type. This is called a binary MERA. This is a so-called ternary MERA because it always maps 3 sides to 1. This is an example for 2D, and always, okay, you find this kind of structure, just that the number of different layer transition maps depends on the specific case. Okay.
Sorry, Thomas. Yeah. Sorry to interrupt. Could you clarify again how do we pass from the first graph to the next one with the channels?
You mean here, or?
Yeah. How do we see this stuff?
Okay. Yeah. Yeah. So the idea would be that you start. So this lowest layer, let's call this layer capital T, and we would start from some reference state. Let's say just initializing some 0 states. All 3 of these sides, yeah, initially some 0 states. Okay, this would be our row T, and now we implement either this transition layer or this transition layer with equal probability.
But how do they correspond, these 3 triangles, blue triangles, with the first triangle that you have in the upper graph?
Say again the question, I don't understand.
How do they correspond, these 3 triangles there with the triangle that you were showing me in the first graph there? Mm-hmm. Yes.
Yeah, so these 3 guys are these 3 guys.
Ah, okay.
Yeah. Yeah, and these 2 unitaries are these 2 guys. Yeah.
Okay.
Yeah.
Okay.
Yeah, and in practice, what you would do on a quantum computer is you would basically, to implement this channel, for example, you could just flip a coin, and you either implement this guy or this guy, and then you just repeat this measurement many times, right? And then you get this channel. Okay, so here's some first benchmark simulation just done on a classical computer for the transverse Ising chain, which is sort of the most forgiving model you can look at. And yeah, so it's also the simplest example of a phase transition. So you have a competition between these, so these are Pauli matrices, sigma z, sigma z. This tries to align 2 neighboring sides. And then you have this competing term, which corresponds to a magnetic field in the x direction. And this tries to align the spins into the plus x direction. So you have a competition between these 2 terms. And you get a phase transition at the critical value, which is g equal 1 here. For when this term is stronger, you have this ferromagnetic phase, where you have sort of all spins up or all spin down. And then if you go to, so you have a Z2 symmetry here. And then if you go with g larger than 1, then you get this paramagnetic phase where the spins are polarized basically in the x direction. And you have different types of excitations there. And yeah, so we simulated here just using bond dimension 8, which corresponds to 3 qubits per renormalized sides. And we only used 2 Trotter steps for each tensor, right? So there was this picture, right? This picture, you would just use 2 Trotter steps to implement these tensors. Yeah, and then you see here the convergence. So let's just look at the blue line. You see the accuracy of the energy density. So this is the exact one. This is the one in this Trotterized MERA. And you see it goes down to like 10 to the minus 7, so very precise. Of course, the gradient is also reducing. And then this plot shows sort of the results for the optimized MERA as a function of the field strength. And you see, and there's a comparison of this MERA for two different choices of this number of Trotter steps with the full MERA. So the full MERA is basically the same MERA where we don't put this Trotter structure, but allow for arbitrary unitaries and so arbitrary unitary disentanglers and isometries where we don't put this Trotter gate structure. So that's this yellow line, and then we get pretty close. Just with one or two Trotter steps, we get pretty much to comparable position.
How is the comparison in running time?
Running time, so that's a good question. I mean, war clock time, I can't really say. But the F-MERA optimization is more efficient because there you have this, you can use this local optimization for each tensor, whereas for the T-MERA, we can just do sort of a gradient descent, right?
Okay, and in memory, because the full MERA is kind of very heavy, no?
Yeah, the memory cost would be smaller for the T-MERA because you have this Trotterization, yeah.
Do you know how much?
Yeah, so you can just, I mean, it's like instead of having like a chi squared by chi squared unitary, you have T times 2Q of the qubit gate. So, I mean, it's a simple calculation. Yeah.
But the memory cost is
but it's not essential, I would say. It's not
memory
essential.
cost is bottleneck in the intermediate contraction.
Sorry?
There will be memory cost in the intermediate tensor network contraction. And if you do it classically.
Oh, yeah, if you do it classically.
Yeah. So
classically.
rather than memory cost of saving all the data.
Yeah. That's actually a good question. Would this that we were also thinking about? Would this even make sense in a classical simulation? And I think there are some arguments because you could basically use, for example, an MPS to also the MPS way of contracting this instead of doing it exactly, and then you would gain something. But of course, you make another approximation.
Can you prepare that on a quantum computer?
Say?
Can you prepare that on a quantum computer?
Prepare what?
The circuit.
Yeah, we're doing this on a quantum computer, yeah.
Okay.
Yeah, we're actually doing it right now on ion trap quantum computers. Okay, so maybe just to worry about this peak. This peak here is all of this. So here you have the lowest accuracy at the critical point, which is quite natural because there you have the most entanglement. Okay, here's a little bit about the costs. So the time complexity to evaluate the energy density is, as we already discussed, linear in the number of Trotter steps and linear number of layers. And then, of course, we have sort of the same number of Trotter gates times Q. So if you want to evaluate the gradient for all Trotter gates, then we need to multiply these two numbers, and we get this square scaling in the number of Trotter steps and number of layers. But still, sort of, you get to pretty relatively big MERA with small costs. So for example, if say we have a 1D binary MERA with bond dimension 8, this means 3 qubits per renormalized site and 6 layers, 2 Trotter steps for each tensor, then you end up just needing 12 qubits on a quantum computer and 48 layers of such 2 qubit gates. So it's pretty benign, and it doesn't change much as you go to 2 dimensions. Just the number of qubits will increase. And of course, like, so this is numbers of layers, not total number of gates. So of course you have to multiply or something. But it's not like crazy numbers. So it's conceivable that one can really do something useful at some point with improving quantum computer quality. Okay, then one thing I omitted so far is that, of course, all measurements on a quantum computer are stochastic. So in the measurement on a quantum computer, we don't get the energy like expectation value or the gradient of the expectation value. We get just, for example, one eigenvalue of the Hamiltonian, right? So we get sort of the measurement results from quantum computer are stochastic, and you have to average many repetitions sort of to get an estimate for the energy expectation value or the gradients. And yeah, so the number of samples you will need to get an accuracy epsilon scales as 1 over square root of the number of samples. And so we have to take this into account for the quantum cost, right? So we have this quantum cost, and we have to sort of divide by epsilon squared. if you want to invest in deeper circuits, then you could use quantum amplitude estimation. So there you would sort of repeat the same circuit multiple times in order to reduce the total computation costs, like at the expense of having like larger circuits. Okay, and we take now this measure here for the time complexity to compare a classical to a quantum simulation. So these 4 plots here are for different models, different spin chains, which actually have nice physics that will also be interesting to discuss. But let's just look at sort of the cost scaling. So what you see here is again the accuracy of the energy density as a function of the simulation cost, where the black lines are the classical sort of full MERA simulations, where we just vary here the bond dimension from dot to dot. So chi is increasing here always by 1 along this line, and you see sort of a power law improvement of the energy accuracy as you increase the computation cost. And now for the Trotterized MERA on a quantum computer, what we can vary is the number of qubits per renormalized site. That's basically the bond dimension, right? So bond dimension is 2 to the power of q. And we can vary the number of Trotter steps. So along this blue line here, which corresponds to 2 qubits per renormalized site, we always increase the number of Trotter steps by 1, and you see sort of a convergence or saturation sort of energy expectation value. So at some point you switch over from q equal 2 to q equal 3 and continue it again, so start to saturate, then you switch over to q equal 4 and so on. And if you follow sort of this line, you again get some power law scaling, and you see that the classical computation cost sort of, or so the accuracy here improves slower in the classical simulations compared to the quantum simulation. So we claim that, okay, we already see in 1D some moderate polynomial quantum advantage, which of course, if you take into account that in 2D these classic contraction costs go with such a high power in the bond dimension, we expect a much bigger separation than for 2D models. It's just very, right now sort of we're not able to work out the scaling in 2D because the simulations are so expensive. Yeah.
Could you just sketch where are we in the phase diagram of these 3 models?
Okay, so this model, thanks for the question. Actually, I want to show the slides. Let's just look at this bilinear biquadratic spin 1 chain. So you have a competition between this so-called bilinear term, so that's nearest neighbor spin-spin interaction, and a nearest neighbor interaction squared. That's the most general SU2 symmetric spin 1 chain you can have. And you can parameterize the relative strength by this angle theta. And this model has, I think, 4 critical points. And these are 2 critical points with theta equal minus pi over 4 and theta equal pi over 4. So if you want, I can show you quickly, not sure how quickly get there, the phase diagram. Maybe not a good idea. So here's the, oops. Yeah, here's the phase diagram. So you have, we looked at this point, so this so-called Ullmann-Ley-Sutherland point, theta equal pi over 4, between the critical phase and this famous Haldane phase. So this was for the known, because like Haldane proved something about the gaps in these Heisenberg chains at theta equals 0. And then you have another critical point, which is beta ansatz integrable, here the so-called Takajan-Bawejan point at theta equal minus pi over 4. You have a dimerized phase and different phase. And we looked at these 2 points here. So the critical points where you have the most entanglement. Okay. All right. So in this
on the previous slide, maybe I missed it, but here you're taking into account the sampling complexity also, right?
We're taking into account the sampling complexity. Yeah.
And this is for a single evaluation, or is this actually optimizing? And you were mentioning before, like with the quantum computer, you have to run some gradient descent. Well,
we plot. Good point. Yeah, we plot. The cost is just the evaluation cost sort of for the gradient. So maybe actually that's a good point. Maybe you could argue it's not a fair comparison because you have different optimization algorithms in classical in the classical simulation. Okay, but one nice feature also we noticed, which is also not too surprising, is that the rotation, so if you parameterize these two qubit gates by rotation angles, then it turns out that these rotation angles are tightly peaked around 0 rotation angle, which is very nice for the experiments, because if you implemented two qubit gates just with this, if you just have to implement two qubit gates with small rotation angles, then you can do this faster, right? Because a gate means time evolution, or you spend the same time but then get a gate with higher fidelity. So it's good sort of for the experimental realization if these rotation angles are indeed small. And so we also had some additional tests sort of where we just added here to the energy functional an additional penalty term for large angles. And what you see in this plot is how the average rotation angle goes down as we increase this coefficient kappa here, and how as a reaction sort of the optimized energy goes up. And you see that you can reduce sort of the angles quite a bit, at least a factor of 2 or something, before anything relevant happens in the energy expectation values. And one can play sort of further tricks in order to exploit this fact that you have small rotation angles. Okay, so we've done first experiments on quantum computers, also ion-trap quantum computers at the Duke Quantum Center. So this is with Marco Cettina and Ken Brown. Yeah, this is my former student, Chang Miao. So these are so-called surface ion traps where you have a chip and on top sort of electromagnetic fields confine ions which are also repelling each other, so that they form sort of a chain, and you can use also the vibrations, also laser beams then, and the vibrations of this chain in order to implement two qubit gates. The computational states 0 and 1 are encoded in two hyperfine states of these ions. And yeah, so then you can do all kinds of...
That's a lot of ions, or is that an artist's impression?
No, that's yeah, but that's not typically what you would have if you really want to do digital quantum computation.
I was going to ask. Okay, that's,
yeah. So
they can load so many atoms, but it's just to show off how many atoms.
Yeah, realistically, for quantum computation, they're right now like maybe they have 20 qubits roundabout. Yeah. Well-controlled qubits. Okay, and again, sort of here's now experimental results for the same model again, the transverse Ising model. And yeah, I told you that there's this phase transition at g equals 0, and what is plotted here is the magnetization in x direction. So yeah, I should mention, here we just sort of put a pre-optimized Trotterized MERA, so we optimize it on a classical computer, and we just want to evaluate expectation values on a quantum computer, because like still it takes time, and these ion trap people also have other other stuff to do, and then sort of running sort of optimization forever. So we just sort of pre-optimized the MERA and just evaluated on the quantum computer the expectation values for energies, some correlation functions, and here for the magnetization. And you see nicely in the magnetization this transition from the ferromagnet to the paramagnet with pretty good accuracy.
But this is without error mitigation, right?
This is without any error mitigation, yeah. Okay, and what we are doing right now is also we would like to sort of show this logarithmic scaling of entanglement entropies that you have at the critical point, right? So if you have g equals 0, then the entanglement entropy in the system scales with the log of the subsystem size.
Sorry, can you give us an idea of the circuit depth and these?
Sorry, say again?
Of the circuit depth necessary to...
Yeah, so here we have 5 layers. So this means that the circuit has a depth of just 10 layers of these of 2 qubit gates, basically.
Okay.
Yeah.
Did you try also non-local gates? I mean, things beyond nearest neighbors, because with an ion trap.
Yeah. Actually, we tried. So what we tried is, instead of having this brickwall structure, we tried sort of a random covering, if you want. But like on classical benchmark simulations, we didn't see any difference in the quality that you get. But there are also multi-qubit gates, so you can use these MERA gates, and this would be something that you could still try to sort of enrich the expressiveness sort of of the network. Okay, what you're trying to do right now is measure such entanglement entropies and show that you get this log scaling. So one thing you could do is what nice thing here is in the MERA, you actually don't need to, in order to evaluate entropies, you don't need to, or these bipartite entropies, you don't need to prepare the MERA on the full system, but you just need to prepare sort of, something like this and then measure, so do a tomography on these sites here. This would give you, in some basis, sort of the reduced density matrix for the left half. So you sort of don't need to implement actually these gates because they just correspond to unitary transformation on the left half, which doesn't change the entropy.
Sorry, what do you mean by tomography in this?
Yeah, tomography just is a word for determining the reduced density matrix. Because on the quantum computer, the only thing you can do is basically local measurements. Right? You can measure, like, is this qubit in state 0 or 1? And so you need, in order to get a reduced density matrix, you basically have to measure a basis of operators. Like if you measure an operator basis, you can expand density operators operator basis, and if you know all expectation values for the operator basis, you know the density operator. So that's called tomography. Yeah. Okay, so this is still in progress, and I should also mention that in a group of Michael Voswijk at Continuum, they also implemented this experimentally with another ion trap system, and what they measured nicely is sort of correlation functions, and they were able to show also with a pre-optimized MERA, and they really saw sort of this power law decay of spatial correlations. Okay, yeah, so one more thing you might worry about is noise, right? Of course, these, as you already pointed out, these quantum computers don't implement our gates exactly. So what's the influence of noise here? And it turns out that this ansatz is in itself already sort of noise resilient in the following way. So you had already seen this formula here, right? So this is again the energy expectation value, and we expressed it as this sort of starting from a reference state at the last layer, sort of, and then applying these layer transition maps, which sort of always bring us up one step. So we have T of these layer transition channels, and then we just evaluate the expectation value of a local interaction term, and that gives us the total energy expectation value. Now if we have noise, so we have some noisy unitaries, then this means that we don't implement these layer transition channels exactly, but some sort of noisy version of it. And let's say we have some control over the noise, so the difference is some small number epsilon here. Then first of all, the ansatz will still be variational, so you could vary that. Okay, as soon as you introduce noise, the energy expectation value that you get might not even necessarily be above the ground state energy, but that's still true because you can still ignore sort of everything that's outside the causal cone. You can still ignore because for any channel, sort of any channel maps or the joint of the channel maps identity to identity, so you can still, even if you have put noise on these tensors outside the causal cone, they don't influence this expectation value. And then inside the causal cone, you can bound the error that you're making. And so this is due to analysis by Kim and Swingle. You just have to sort of use a telescope sort of decomposition of this difference, and you get that the error scales just linearly in the number of layers, which means logarithmic in the total system size. And turns out that this bound is actually too pessimistic, because if you have a gapped system, so gapped means that you need to pay a finite amount of energy to go from the ground state to an excited state. These we call gap systems. And in these gap systems, you have always a power law decay of correlation, sort of an exponential decay of spatial correlations in the system, which implies that you don't need to implement sort of an arbitrarily deep MERA here, so you can choose, in this case, the number of layers independently of the system size, because you have this exponential decay of correlations. At least, I mean, I'm not sure whether there's a strict proof of that, but at least morally that's true. Actually, there's, because you can, we know that MPS sort of are able to approximate these systems, and the MERA with a finite bond dimension is basically an MPS. Okay, and then you might worry about the critical points, so these transition points where we get then power law decay of correlations and this log scaling of the entanglement entropy. But yeah, so you can argue that even then nothing bad happens, because that's maybe just something that the physicists can appreciate. So if you look at the corresponding field series, you find that the scaling dimensions of all operators other than the identity are positive. which translates mathematically into the fact that the spectrum, or that these quantum channels here are gapped, right? So if you, each channel always has at least one eigenvalue, which is 1. And now if you look at the next one, so the next largest eigenvalue, this will then be smaller than 1, right? And you can then bound sort of what you get sort of for this difference here, you basically get the decay of the deviation as you go layer by layer. And so in the end, what you sum up is sort of a geometric series of epsilon to the power of tau, lambda to the power of tau. And so you get this much better bound for the error scaling, which is again sort of independent of the system size and the number of layers. Okay, so maybe in the last minutes, or any everything's fine? Okay, so as a last topic, I quickly wanted to mention the issue of Barren plateaus. So maybe some of you haven't heard of this, so at least I think it's good to know what the idea is, because there are a lot of papers in the quantum computing community on these Barren plateaus. And I think it's also a nice mathematical topic. So the question is the following. The question is, if we have a tensor network, for example, here just a big brickwall tensor network, can we optimize in the sense that can we find a good initial point, or can we do gradient descent really? We know, okay, there will be some optimum, right? So, but what can happen is that your energy landscape basically becomes flat, except for some points, a very rare point where then the ground state is located. So what can happen is, and that's called the Barren plateau, that if sort of you choose a circuit here which is deep enough, what happens is then that the energy gradient, or I should say the average amplitude of the energy gradient, decays exponentially in the system size. So in other words, if you sort of parameterize your circuit here by angles, almost everywhere this landscape is totally flat. And if you now do use such a variational quantum algorithm to optimize this tensor network, you would basically end up doing a random walk on this flat surface, because you only evaluate the energy gradient to a certain accuracy. And yeah, this will just kick you around on this basically flat landscape, and you will never find this point here. Yeah, and so the question was, okay, does this phenomenon also occur for the tensor networks? And turns out it doesn't, maybe not surprisingly. So we just looked at this question, how does the average energy gradient amplitude scale with the bond dimensions of these tensor networks and the size of the system? And we're able to show sort of that in these cases, you don't have, so for a matrix product state, 3 tensor networks in the MERA, you don't encounter this Barren plateau problem, and we were even able to derive how exactly the scaling works. Where this average here, I mean, is that we take the Haar average over all the unitaries in these tensor networks. Right, so in the MERA, we had discussed it by definition, all these tensors are unitaries or isometries. In the MPS, in principle, they are not, but we have this gauge freedom that we discussed a few times during this week. So you can use sort of the right gauge for your MPS, then all these tensors basically become isometries. In isometry, you can always write as a unitary where you sort of come in with some reference state. And so in the end, everything here is isometric or unitary. And the average then is the Haar average over these unitaries in the tensor network. Okay, and the first step, just to explain very shortly, is to express the energy expectation value in a convenient form. So let's say we just consider the variation of the energy expectation value with respect to one of the unitaries that we have in a tensor network. So this would be the local energy expectation value for an MPS, where we just, in this case, just look at the single side term. So we can write this always in this form. So we can decompose this tensor network of the expectation value into one part y here, which contains the Hamiltonian term and some of our MPS tensors. Then the unitary that we're currently changing, this would be this u, and then this part x here, which contains the rest of the network. Okay, and once you have this form, then it's, so here's just a picture that the same is possible for MERA. All right, so you have this y term, the unitary that we're changing, and the rest here would be this tensor x. And then the first step is to get the gradient. So the gradient in the embedding space of these unitaries would just be this, right? So you take the derivative of this network with respect to U dagger, then you get to this network. And then if you want to do sort of Riemannian optimization, so if you want to project the gradient onto the tangent space of our unitary manifold here, then we get this additional term. But it's also not super complicated. And now, okay, you can evaluate the average gradient. First of all, is 0, right? Because it's odd powers in the unitaries. So the average gradient is 0. Hence, you can quantify the gradient variance by this expression here. And if you evaluate this, again, sort of using this Weingarten calculus, you find this funny combination here of these x and y tensors. Okay, and now if you look at this first case, so we have this brickwall circuit, and let's say we simplify even more. We say we just have one big, if you have L sides here, one big d to the L times d to the L unitary, which parameterizes our state. Yeah? So we say our ansatz is just totally generic. We say we start in some reference state, and then we apply this big unitary, and now we evaluate. So want to evaluate the average energy gradient for this state here with respect to variation of the unitary U. Then you find this exponential decay. Yeah? So maybe to see this, the energy expectation value has again this form that I put here. So we have x is now just our initial reference state. Y here is the Hamiltonian. Yeah? Y is the Hamiltonian, and U is this big unitary. Okay. And now if you plug this into this formula, so in this case, this formula simplifies a little bit. You just get sort of these variances, if you want. So the first term here is this trace of x minus 1 over n trace x squared. X is this reference state, so you get 1 minus 1 over n. Then here in this term, y is the Hamiltonian, so you just get, if you assume that trace of Hamiltonian is 0, you get just trace of Hamiltonian squared. And the only important thing that remains is this prefactor. N is now here the total Hilbert space dimension, so this d to the L. So we get the scaling d to the minus 2 over L. So this is called the Barren plateau because the average gradient amplitude or the variance of the gradient is exponentially small in the total system size L. So that's this Barren plateau. And then we sort of analyze this for matrix product states, MERA, and so on, and we're able to derive the scaling of these gradient variances. In the MPS, so this here is the variation. So we just look at one local interaction term, and we vary with respect to another unitary at site. So this x at site I, this x at site j. And it turns out that, okay, you get some polynomial in the bond dimension, and this gradient amplitude would decay exponentially in the distance of points I and j, which sounds kind of bad, but this is, of course, not an interesting problem, right? We want to have actually an extensive Hamiltonian, so we have a sum over interaction terms on all bonds or on all sides. And then, of course, sort of you sum again this up in some sense, so you get, again, sort of a geometric series, and you get something, a term that is independent of the total system size, leading term that's independent of the system size.
Can I ask a question? So you are parameterizing over this unitary, so these are the variables. So why is the gradient number and not a vector?
Great. Now I'm just I'm computing the variance of the gradient.
Okay, so it's just the sum of the variances of the individual elements.
Yeah. So how I quantify the variance of the gradient. So I'm saying, so G is the gradient, right? You're right. It's sort of, in this case, would be an operator, right? And I'm taking trace of G dagger G. Yeah. And the motivation here is basically that you could, if you would parameterize this U here by rotation angles, right? Then this expression would correspond to the average rotation angle, actually, rotation angle squared. Yeah.
I have a question. Has it something to do with the quantum natural gradient?
Say again?
Has it something to do with the quantum natural gradient?
Actually, I don't know the term, so I have to discuss.
I think the same as Riemannian gradient.
It is called the Riemannian gradient, yeah.
Yes, but quantum quantum natural gradient is a Riemannian.
I think so.
It's actually the Fubini study metric on the basic states.
Yeah, I think the same as the Riemannian theory.
Okay, I should finish in a few minutes. So just to conclude here, for the MERA, we find something similar, just that if you consider the derivative with respect to a unitary in layer tau, then you find sort of an exponential decay in the layer tau, right? Which is still acceptable because this is logarithmic in this, the last layer would be logarithmic in the system size. And of course, in the first steps, you would probably start optimizing the lowest layers where this is sort of order 1 in the term. So you still have no Barren plateaus. And you find nice coincidence of these analytical results with numerics. Okay, yeah, so we analyze this for all kinds of MERAs. If you want, I can, in the discussion, could explain you roughly the proof idea. But for now, I would like to conclude. So I described first a variational quantum eigensolver based on MERAs, where we trotterize these the unitaries and isometries in the network. We need, if we use translation invariance, a system size independent number of qubits to implement this. And in benchmark simulations, we found sort of the polynomial advantage over classical simulations. I described you sort of very shortly some first experiments on isometric quantum computers. We talked about the fact that these MERA are actually noise resilient. And we talked about the Barren plateau issue, which it turns out you don't have for these MERA, and also you don't have them for MPS or tree tensor networks. All right, thanks.